Have you ever deployed a Logic App workflow only to find out your HTTP requests failing in production? Picture this. Your integration is running smoothly in testing, but in the real world, you're missing critical data because the built-in retry policy only handles a handful of error codes. Your customer data isn't syncing, transactions are being lost, and your team is scrambling to fix it. Here's the thing. Azure Logic Apps default retry mechanism is like using a hammer when you need a Swiss Army knife. It's too basic for real enterprise integration needs. In this video, I'll show you how to build a custom retry mechanism that gives you complete control over retry behavior. Whether you are handling financial transactions, syncing customer data, or managing critical business processes, you need a retry strategy that won't let you down. Let's dive in and build one together. When working with HTTP actions in Azure Logic Apps, many developers initially rely on the platform's built-in retry policy, assuming it will handle all potential integration challenges. However, the reality is far more complex. Let's dive into why the standard retry mechanism falls short in real-world enterprise scenarios. By default, the HTTP action in Logic Apps provides a retry policy that seems straightforward at first glance. It automatically retries requests for a limited set of HTTP status codes, primarily focusing on temporary server-side errors. Specifically, the standard retry mechanism typically targets status codes like 408, request timeout, 429, too many requests, 500 series, server errors 500, 502, 503, 504. While these cover some common transient errors, they represent just a fraction of the potential issues you'll encounter in enterprise integration environments. Consider a scenario where you're integrating with a third-party API that returns unique error responses or has specific error handling requirements. The standard retry policy becomes woefully inadequate. Think about real-world integration challenges. What happens when you receive a 400-level error that's technically retriable but not captured by the default mechanism? Or when an API returns a custom error code that doesn't fit into the standard retry categories? These are the scenarios where enterprise-grade integration demands a more sophisticated approach. Many organizations discovered that their integration workflows require nuanced retry strategies that go beyond the one-size-fits-all approach of the standard policy. You might need to retry on specific custom error codes, implement different retry logic for different endpoints, add sophisticated back-off mechanisms, or maintain precise control over retry attempts and intervals. The limitations become even more apparent when you consider the diverse ecosystem of cloud services and APIs. Each integration point might have unique failure modes that the standard retry policy simply cannot anticipate or handle effectively. By understanding these constraints, you'll realize why custom retry mechanisms aren't just a nice-to-have feature. They're often a critical requirement for building robust, resilient integration solutions in Azure Logic Apps. In my upcoming demonstration, I'll show you exactly how to overcome these limitations and create a retry strategy tailored to your specific integration needs. I'll transform the standard, rigid retry approach into a flexible, intelligent mechanism that can handle the complexities of real-world enterprise integrations. When you're building an enterprise integration that connects multiple critical systems, your workflow isn't just a simple request-response mechanism. It's a complex dance of communication between different systems, each with its own unique challenges and potential points of failure. Let's break down the real-world scenario that makes robust retry mechanisms absolutely essential. Think of these as the hidden challenges that standard retry policies completely overlook. Network instability. In any distributed system, network interruptions are not just possible, they are inevitable. Consider a scenario where you are processing a batch of financial transactions. A momentary network glitch could interrupt your API call, potentially causing missed or duplicated transactions. The standard retry mechanism might miss critical retry opportunities, leading to data inconsistencies or service disruptions. Transient service unavailability. Cloud services aren't immune to temporary performance issues. Imagine an Azure function or a third-party API that occasionally becomes temporarily unresponsive. The reason can be numerous: short-term resource constraints, ongoing updates, or unexpected load spikes. Your retry mechanism needs to be intelligent enough to distinguish between a truly failed request or a temporary hiccup. Okay, then let's dive deeper into real-world scenarios. Complex error response. Not all errors are created equal. Enterprise APIs often return rich, detailed error responses that go far beyond simple HTTP status codes. You might receive detailed error messages with specific retry recommendations, throttling information with precise retry after guidance. A sophisticated retry strategy needs to parse and respond to these nuanced error scenarios, something that the default Logic Apps retry policy simply cannot do. Compliance and reliability requirements. In industries like finance, healthcare, and government, every transaction matters. A missed or improperly handled request isn't just an inconvenience. It could have significant legal or financial consequences. Your retry mechanism becomes a critical component of your overall system reliability. This is where a custom retry mechanism transforms from a nice-to-have feature to an absolute necessity. Your ideal retry strategy should be intelligent, understanding context beyond simple status codes, adaptive, adjusting retry attempts based on error type, transparent, providing clear logging and tracking of retry attempts, and configurable, allowing fine-grained control for different integration scenarios. In the next slides, we'll dive deep into how you can design and implement such a robust, intelligent retry mechanism in Azure Logic Apps. We'll move beyond the limitations of standard policies and create a retry strategy that's as dynamic and resilient as your enterprise integration requirements. So let's jump into the practical implementation of such a retry policy, and then we are moving to the Azure portal. Okay, let's dive into details of the implementation. We are in the client implementation. The Logic app which I have created implements the HTTP client. And the core element of the retry mechanism is the scope. The scope contains the do until retry loop. In the retry loop, I have placed the delay action. The delay action is inside the condition action, which checks that the loop is not the first one to run the delay. So it's obvious that we shouldn't apply the delay at the first loop. The first loop just goes to the HTTP request action, the third element of the retry logic mechanism. So it goes directly to the HTTP request without delay, and only in case HTTP request returns the error, and we will repeat the run, on the second loop we'll have to apply the delay. So this is why I have the condition action here. When it comes to delay, it implements the exponential backoff logic. So if we have a look at the count of seconds expression, and I specified seconds here. So the count of seconds will depend on the iteration of the do until action. And this will be found with use of iteration indexes function, the standard function in the Logic app which returns the number of iteration in the loop. very useful. And then I use this iteration number and multiply this by 2 to increase the number of iteration. And then I apply addition of the random value from 1 to 5. You're free to use your own values, which you prefer. So this one implements the role of jitter to the exponential backoff logic. So instead of standard intervals between requests, we have some level of randomness, which help us to allocate the request of multiple instances of the client more evenly. Okay, nothing more to say about the delay, exponential backoff. Next, as I showed already, goes the HTTP request action. I use another logic app as a service, as an endpoint to the service in the cloud, which simulates the endpoint which the client communicates with. This service has some portion of logic to return errors. Next element in my retry policy implementation. This is just a variable, and the variable is called requires retry, and it's obviously that it will be used further in the until loop to check whether it's necessary to repeat the loop, whether it's needed to continue requests to the service, depending on the status code returned by the HTTP request, and additional logic which we may implement and which will include analysis of more complex data. Okay, but to the logic applied to this variable parameter, which I have defined and I use in calculating this requires retry variable. The parameter is called retry responses, and it's of array type, contains integers, and it actually contains status codes returned by the HTTP request. The logic behind this is that I need to repeat the request to the HTTP endpoint if the returned status code is one of this. Pretty simple. And these two, 408 and 429, are status codes used by the standard retry policy, the retry policy implemented by the HTTP action. Other codes are just custom codes which may appear here in this array due to specific behavior of your service endpoint. So if the service endpoint which you are going to communicate with has some implementation specifics causing this service to return non-standard status codes, you may include them here. If you want to interpret this code as error and you want to repeat the request to your service. Okay. Next element in the retry policy is switch. It's empty now, but you may build your logic here, and this switch may analyze the status code of the HTTP response, or, for instance, if your service returns a complex response, textual response, with some business error codes. So you can build your logic here where your switch will implement additional analysis based on the content of the complex response and the business error codes, for instance, not related to the HTTP response status code. And we came to the last step. This is how the do until action is implemented. And first of all, you will have to take care about standard parameters where you define the maximum count of iterations which your do until action will do. And the timeout, which is applied a similar way, but it's not about count of loops, it's rather about the duration of time. So the first one which is achieved works, either the timeout or the loop count. The work of the do until loop will be finished when one of them is reached. And you have to, of course, specify the loop until logic. So here you define the logic which will stop execution of loops of this action. And here my logic is very simple, because I just use the variable requires retry and I apply negation to this Boolean value. So if it doesn't require retry, I terminate the do until actions. Pretty simple. Okay, here the scope is finished. So I may close my scope. But you see that there are other actions here. This one is used to analyze the result of the retry scope. So I use the result of the scope here. And the scope will return the aggregated result for what we get after execution of loops. As I mentioned, the loop may be terminated by reaching the maximum number of iteration regardless of the result of the HTTP request action. The same way about the timeout, again, regardless of the HTTP request action. So we need to differentiate these situations. Or the scope may be finished because we've got the successful status code from the HTTP action, and then the loops were terminated and we went out of the scope. Okay? And then based on this logic app just returns the result to the outer scope. So this is the condition action, which have two checks joined by AND logic. The first one analyzes the requires retry variable. If it's false, this means that we went out of the scope by successful, or maybe not successful, but by the result which doesn't require more iterations. So it may be an error returned by the HTTP action, but the error which will not be fixed by a repeated request, right? And the status code itself of the HTTP request, it must be less than 400. The 400 is first error status code, so 400 and higher are error codes. Having these two checks analyzed, if both return true, we don't need to make retries, and we've got the status code less than 400, then the response is okay. Otherwise, the response is error, right? And the error is, while the okay is pretty simple situation, because we will return the real response status code of the HTTP action. It's successful. And the body returned by the HTTP request what we wanted to get. The response error is a bit more complex because we don't know what kind of status code would be returned. It may be error, or maybe something which is not interpreted as standard error. So because of that, the status code here is not just the value but the logic which checks that if the status code is less than 400, then we use 500 instead, because the status codes below 400 are not errors, but we want to return an error. So we use 500 as a sort of generic error, okay? And if it's not less than 400, then we will return the actual status code. This helps us to get the more real error. And there is also a body response. It may be, of course, much more complex, but the simplest form is that it returns the response of the HTTP request. Let's assume that the HTTP, in case of error, the HTTP request returned us some complex error response with details, with definitions of what we should do to fix it. So there are various different options of what can be returned. We place it here. I put the HTTP request status code here, but again, it may be some business error code assigned by the system which we request. Okay? So This is basically the retry logic which is used, and then we will go to the service. I want to show you the service because it has a bit of logic here, and the intention was to make it working so that it will return error status code for first requests to the service. And eventually it may return a successful status code. So with this behavior, we simulate a situation that the client makes a request, gets an error first. It may take a second request and get an error again. And then on a third attempt, it will get a successful request. So this is basically the intention to simulate such a situation. And I just made a simple implementation of this behavior with use of time delays. So the trigger is the standard HTTP request trigger, and the schema defines that the timestamp attribute should be placed here. So I rely on the timestamp attribute, which contains the timestamp of sending the first request. And then this variable uses the calculation. So the value which is set to the variable is the result of calculations using ticks on the result of the function UTC now, the current timestamp. Another ticks, I use the value of the timestamp attribute, but not the exact value. I add 11 seconds to that timestamp with the function add seconds. And then I subtract these two values of ticks, and in the beginning it will return a negative result, negative, less than 0. And after 11 seconds it will return 0. And after more seconds the result will be positive. So I analyze this in this condition action. So time delta, if it's less or equal to 0, then the response returned by this logic app is error. And when the time delta becomes greater than 0, it starts returning OK result. Error and OK means that here I return status code 201, and here I return 299 and some body content with some detail about the error. 299 is of course not the real status code, it's just to show that we can implement the retry logic reacting to acceptance of such status code. Okay, then let's go back to the client logic app, and it's time to try it out in the test. After all these explanations, let's see how it works in practice. Let's jump first to the service logic app, which will simulate my service endpoint, and I'll see what logic is used for calculation of delta time. I use 11 seconds, so the client should send repeated requests to this service within this time period. But after 11 seconds, this service will start responding with a successful result. Looks good. The client. For the client, I need to check count our iterations, and I will increase a bit. Let's set 7. The timeout is big enough, 20 minutes is more than we need. I'm going to test now how the retry policy will work without expiration, without the time expiration. So 7 iterations is okay. So I'm going to run this logic app with a payload. The payload will be very simple. Just use the ID attribute, click run. Let's see what is going on. The logic app is still running, and we have a result. So let's go step by step. I'll explain what has happened. An additional attribute, timestamp, has been added, and the timestamp was the result of function UTC now. So it was the moment when the logic app has been started. init request retry is just a variable without the value now. We see that the execution took 13 seconds and do until loop did 3 iterations. So on the first iteration, the delay has not been applied. The request has been done to the service endpoint, and it returned an error with the status code 299. If you remember, it was the status code which I have set in the service logic app. So everything is in accordance with what I have defined. Then the requires retry variable has got the value true, which means that we've got an error and we want to make an additional iteration. So this until made a loop, and we have got the second iteration. Here the delay has been applied for 5 seconds. Then it did next request to the service. In this case, the service responded again with the error status code and the error message. So this iteration looks exactly as the first one. And then we've got the third iteration with a delay 5 seconds again. And the service returned the status code to a 1 this time, and of course without any error message. This was a successful execution. So here we have the termination of do until. This is the result of the scope action in the logic app with the information about how it has been executed. It was done 3 iterations. The status was succeeded. Until is the name of the do until action. And the logic app, according to the condition action, which returned the result true, there were no errors, it returned response OK to 1. If we switch to the service logic app, we will see 3 runs because the client has done 3 requests. The first one it was the JSON object with 2 attributes, ID 10 and the timestamp. So all 3 times the timestamp came the same, and the time delta. This time it's negative, which means that the execution went to the left branch and returned error. The second request has been processed the same way with returning of error. And the third request, I'm going to show you what we've got for time delta. The time delta became positive, which sent the execution to the right branch, and the logic app returned successful status code to 1. So this is what it looks like on the service side. And I want to check also how this retry policy works with the expiration of time. For testing of this test case, I'll switch to the designer, and I want to do some adjustments in the do until action. We should set some big number of iterations, because we're not going to go out of the scope by exceeding the number of iterations, but rather I'm gonna set a short time period, and I will use 9 seconds here. I will save changes, and I'm running the logic app with a payload again. Next ID, run. Let's go to the history. still running. Let's check the result of the HTTP request returned on the last iteration. This was a request. The response was successful. As a next test, I want to check how it will behave if do until loop will terminate by timeout. So I will go to the settings of do until loops, and I have to increase number of iterations to something that will not be reached, something like 30. I need to shorten the time delay here because I want to get the timeout faster, something like 10 seconds. I save changes, and I want to make a slight change in the service part in the designer. So in the calculation of time delta, I want to increase the number until the result becomes positive, which switches the return from error to successful. So I'll set it to something quite big. Update. I want to save it. And now, if I run my client, let's see what will happen. We need to go to run history. Do until has done 3 iterations. On the first iteration, the HTTP request returned error. On the second, error as well. And third, error as well. 299. And then the do until terminated after third iteration because time expired. Time delay has been set to 10 seconds. So in the scope result, we've got 3 iterations. Status succeeded, and this was status for do until action. It didn't fail, right? Just HTTP request which returned the status code, which means error, but the operation itself didn't fail. So we've got succeeded. Since we have to check the query requires retry. Requires retry has been set to true, which means that we didn't achieve the positive result, the successful result. The logic still assumes that we've got an error which requires a repeated request. But we left the do until, and since the requires retry variable is set to true, this conditional check send us to response error. And the response error in this case returned to the outer context such a result object where the status code is the original status code returned last time by the HTTP action. The response is the body returned by it, and the status code 500 is set by the client logic app by the retry policy because 299 is not technically an error code, but we have to return the error from the retry policy, so we set 500. And the same way the retry policy will behave if I set it up to be terminated by number of iterations. So for instance, if I set 5 iterations here, the time delay, the timeout will be set to 10 minutes, which will not be reached, but the 5 iterations will be reached. So I save it. The service will remain the same. So in order to return the positive, the successful result, we have to wait at least 110 seconds, which we will not reach because we are limited by 5 iterations. And then I run the client one more time. It will be next ID, run. Let's go to history. And now we expect to get 5 iterations here. As expected, 5 iterations have been done. And if we go to the last one, and check the result, it returned the error status code, the error, which means that even though the execution of the do until action has been terminated not by the timeout but by the number of iterations, the requires a try variable still true on the last iteration. Again, because here the HTTP request returned us an error, which we assume is an error. And here on the last check of the result, we get the decision which draws the execution to the error response, where the response is the same as in the previous test. Status code 500 set by this retry policy, and this is the original information returned by the service. I want to remind that the reason we consider that status 299 is the one requiring the retrial is because this code exists in this array of status codes in the variable retry responses. So even though 299, again, technically errors start from code 400 and more, we consider 299 as an error, and it may happen because of a specific implementation of the service. It happens in the real life from time to time, so depends on who has developed the service, whether they follow the recommendations, best practices, and rules of applying the status codes in responses or not. The service may return an inadequate status code, and in addition, to help us, it may return an extended error information in the response body. So this is why we may need possibility to register this status code as an error for this particular service. What we've uncovered today isn't just a technical solution. It's a strategic approach to building more resilient cloud integrations. The standard HTTP retry policy in Azure Logic Apps is too limited. It leaves you vulnerable to integration failures, missed transactions, and potential business disruptions. By implementing a custom retry mechanism, you transform your workflows from fragile to robust. You gain complete control over your handling, intelligent retry strategies, comprehensive system resilience. Your next steps: analyze your current integration workflows, identify potential failure points, design a custom retry strategy, implement and continuously refine. Remember, in the cloud integration, reliability isn't a feature, it's a requirement. Your custom retry policy is the difference between an integration that survives and one that truly thrives. Don't settle for Azure's default limitations. Take control of your integration reliability. If this video helped you, hit subscribe, drop a comment, and let's continue building more intelligent cloud solutions together. Thanks for watching me. See you next time. Goodbye.